In this video, we're going to take a look at the foundations of scientific measurement theory, and this is basically how measurements work. Chemistry is really founded on empirical measurements, so whenever we do any sort of quantitative manipulation of measurements to gain some insight into the way the natural world works, we have to keep some fundamental ideas in mind. And so here we're going to, first of all, talk about the essential components of every measurement, what is built into every single measured quantity. We're going to learn how to apply dimensional analysis using known and unknown variables to solve equations that involve measured quantities, working with units in particular there. We're going to talk about measures of accuracy and precision to talk about the quality of a set of measurements relative to an external standard or variation internally within the data. And then we're going to talk about significant digits, which are really all about expressing results derived from measured quantities with the appropriate level of precision. It's really a measure or a matter of scientific integrity here. We want to avoid expressing results to an overly precise extent that could give readers a false sense of confidence concerning the validity of the results. This is the underlying philosophy of significant digits, which get a bad reputation because of the arbitrary seeming rules involved. I hope to convince you that significant digits are set up the way they are for reasons of scientific integrity, so that our results are as trustworthy as they can possibly be, given the limitations of the measurements upon which those results are based. Let's start, though, with the components of every measurement, what a measurement is. A measurement is a quantitative observation of a physical phenomenon with respect to a given scale, and by the scale here, we really mean the unit defines the scale. So you can think of a measurement as laying down or referring to a specific chunk of a number line where the tick marks on the number line are defined by the units we're using. So there are two components here. There's the unit, which indicates the nature of the phenomenon. Is it a distance or a length? Is it a mass? Is it a speed? Is it a brightness? Is it anything along those lines? Any sort of phenomenon, right? And the size of an increment on that number line where we're pinning the measurement, right? How big is the gap between two tick marks on the number line? The value is what positions the measurement on this number line, on the scale. But an important thing to understand here about all measurements is that the value is never a point. The value is never an infinitely small point. Every measurement we make actually refers to a range of values. Since the precision of our measurements is not infinite, precision is limited, right? Even if you think about something like throwing a dart on a dartboard, the pointy part of the dart has a finite width. So that dart is defining a teeny tiny little circle where it hits on the dartboard, and that circle corresponds to a range of positions, not a single point, infinitely small point position. So value is always a range. This is important to keep in mind, especially when we get to things concerning the precision of measurements and significant digits. We need to keep this in mind. And related to this idea is the notion that all measurements have some degree of uncertainty. Every measurement is a range. So while we'll express measurements using numbers, it's important to keep in mind that any digits to the right of the number we're looking at are uncertain. We don't know what those digits are. And to get a sense of the extent of uncertainty, we'll sometimes use a standard deviation together with the measurement. You'll see this either in one of the two formats that you see here. For example, we might have a distance or length measurement that is 32.813 centimeters. If the standard deviation of that measurement is 0.002 centimeters, we could write that as plus or minus 0.002. In essence, this is saying if we repeated this measurement many, many times, something like 70-ish% of our measurements would fall in the range of 32.815 and 32.811. We can also notate this by putting this 2 in parentheses to indicate that there is an uncertainty of 2, plus or minus 2, in this digit that's farthest to the right. And this graphical representation of the measurement is an important mental image to have. The measurement positions a phenomenon on this number line. The number line is centimeters. Each increment, at least on this scale, is 0.01 centimeters, and so 32.813 plus or minus 0.002 is not a infinitely small point on this line. It's a range of values, and that's what I'm representing here with this blue rectangle. The measurement refers to a range of values. The 2 key pieces here are the units, centimeters in this case, and the value, which is 32.813 plus or minus 0.002, keeping in mind that there's some uncertainty in the value. The system you'll use for measurements 99 times out of 100 in your chemistry course is the International System of Units, or SI system. This includes the metric system as well as a set of base units and then units derived from the base units called derived units that we use for measurements. There are 7 base units. These are actually defined with respect to physical constants that we have measured the values of, like the speed of light and the elementary charge. This graphic from Wikipedia shows you the 7 base units of the SI system and the physical constants that are used to define these. For example, Avogadro's number is used to define the mole, elementary charge is used for the ampere, so on and so forth. I won't go through them in detail. They're listed in this table here. It's worth pointing out, though, that there are 7 fundamental quantities that are associated with these base units: time, length, mass, electric current, temperature, absolute or thermodynamic temperature, amount of substance, and luminous intensity. Other phenomena have units that are derived from these base units. So, for example, something like speed is equivalent to a length per time. So the units of speed would be something like meters per second. And some examples of derived units for other phenomena are included at the bottom of this slide. For example, the Newton is the SI unit of force. That is a mass times an acceleration, kilograms times meters per second squared. There's the Coulomb, which is an ampere, which is a unit of current, times 1 second. And the Pascal is a unit of pressure that is a Newton per meter squared. Pressure is a force per unit area, and so the Pascal has the unit of force, a Newton, divided by the base unit of length, but squared because it's talking about an area. So for any phenomena that are not on this list, we're going to generate units from the base units by multiplying them, dividing them, so on and so forth. The metric prefixes are the second part of the SI system that are really important to keep in mind. The metric system uses this idea that measurements happen at different scales, and a lot of those scales are not human-friendly. For example, if you think about the number of particles in a gram of, aspirin, astronomically huge number. A number so huge that it's hard for the human mind to even wrap itself around it. Metric prefixes make it a little bit easier for us to wrap our minds around very large or very small values. And the way this works is we can think of any value inside a measurement as being some power of 10 times some number between, say, 1 and 10. This is related to scientific notation, which we'll touch on shortly as well. We can take that power of 10 and actually turn it into a prefix that we just put in front of the unit. So for example, if the measurement is 3 times 10 to the third, well, that's say meters, 3 times 10 to the third meters. Let's actually write this out. 3 times 10 to the third meters. Well, instead of having to say 3 times 10 to the third meters or 3,000 meters, which is a bit of a mouthful, we can just take that 10 to the third and we're going to call that the kilo prefix and say that this measurement is equivalent to 3 kilometers. These two expressions of a measurement are saying the exact same thing. They're exactly equivalent, and that kilo prefix is used to refer to 10 to the third power. Kilo is just one of the many metric prefixes that you should familiarize yourself with. And I would say that all of them on this slide you'll see in common use in chemistry. The one that tends to get jumped over is the hecto or hecta. The 10 to the second power is often sort of skipped over. We'll either use deca for just times 10 to the first power or kilo for 10 to the third. Hecto is not super common, but the others you'll commonly see in various contexts. And keep in mind the general idea here is to scale a value generally that's very large or very small to more of a human-friendly level. Some number, the value here becomes a number between 0 and 10, which is very human-friendly.